So in this question, we see these two bodies. It looks like they're identical, and they could be reduced to being at this center of mass. These arrows might indicate that it's rotating like so around a center of mass. It's barycenter. I'm not sure what this indicates. What this indicates, maybe it means it's in free fall. But in that case, it doesn't really matter. It's like the thrown wrench. It's rotating around its center of mass. This thing is rotating around its center of mass. It will behave around this. Now, in the graph below, it looks like there's two things, but if you look at it overall, it looks like this is what's happening. So it could be that one of these graphs is for one of the balls, and the other one is for the other ball, and the straight line I drew is the center of mass. So that could be the case. So we look at our Oizerga. Origin is 0.3, 0.2, 0.10, 0.5, 0.250, so it's right in quadrant 1. Y-axis velocity in normal units, x-axis time. So therefore, we will read anything about velocity and time. The gradient delta v over delta t is the acceleration, and the area v delta t, meters per second times seconds, which is the displacement. So we've kind of unpacked what we think is going on here. Now, two identical spheres, check. Known mass m, we'll give them masses of m. Opposite end of a rod of negligible mass is spun in the vertical plane. Release of the system falls downward as it rotates. So we did figure that system out properly. Shown the graph of the vertical velocity of the two spheres. So what they mean by the vertical velocity is that when we say this ball here, and I'll change the color to blue, it has a velocity at that instant in that direction, but it has a horizontal component and a vertical component. And that's continuously changing. It's going up and down and up and down. All the while, the whole thing is speeding up as it falls. So what they're talking about is just this, the vertical velocity at any moment in time. All right, the student used the graph to make 3 claims. Claim 1, the change in the linear momentum of the center of mass from 0 to 0.5 seconds can be determined. The change in linear momentum of the mass. Does it say... So what we know is at the beginning, the initial velocities are basically 0. This thing is in free fall. So we know that it behaves like this, v equals at plus v0. So if we just know the time, which we can get off the graph or from the question, and we know the initial velocity is 0, we can find out the velocity any instant time, at least of the center of mass. And so if p equals mv and delta p equals m delta v, and we can know the velocity at any instant in time, then we can know the momentum and the change in linear momentum. So it looks like that is correct. Claim 1 is something we can definitely determine. The average applied force on the center of the mass from 0 to 0.5 can be determined. Well, the center of mass, the force, well, that's the rate of change of momentum, which is m delta v over delta t. And wait a minute. We know the mass, and delta v over delta t is the acceleration. We know the acceleration of the center of mass, right? We can forget this whole shenanigans of this thing revolving. We can treat this whole thing as just a body that's in free fall, accelerating at g. So, if we know the mass, which we do, we know the delta v, we know the delta t, of course we can find the average applied force. And the change in kinetic energy of the system. Well, the kinetic energy is 1/2 mv squared. Well, again, we know m and we know the change in v, so we can do 3. I think we can know all 3 claims. Claims 1, 2, and 3. And that would be the correct answer.